is fundamental chemistry and applied innovations with implications for solar energy, photocatalysis, clean technologies, optoelectronics. I am really very thankful to Professor Sapra. When we were submitting this proposal, we have contacted and requested Professor Sapra, and he immediately agrees to be with us during the program to guide our participants in the field of optoelectronics. With this, I request Professor Sapra to please come over the dais. Thank you, sir.
Oh, that will be nice. Yeah. Yeah. हाँ. अच्छा. No issues. Thank you. Thank you. But do you want this mic to be on or is it?
Yes, for Zoom it is.
Okay. Thank you so much. Well, it's been a pleasure, and especially Dr. Zain, who invited me in the very beginning when we were formulating this proposal. So I immediately jumped that yes, I will be a part of it because I've been in Aligarh about 2 years back, and I really love the people, the hospitality over here. So it's a pleasure to come back to Aligarh. Thank you so much for having me here. Now, although I have a talk prepared over here, but I think I'm not going to stick to that. Dr. Zain has many times, in fact, when I was in Delhi and even today morning, he's emphasized that I should cover more of the basics rather than the research. So, इसको बंद कर दूं क्या? हाँ? हाँ, because I hope people online do not have a problem. They are able to hear what I'm saying. If somebody is monitoring the online participants, then you can, yeah. They keep writing things in chat. So, all right. So I'll not be sticking to the slides, and I'll be going more slowly, more with the basics. Also showing you some of the research work. So interrupt me as often as possible. So just raise your hand, or I cannot see online. So if somebody sees online, just let me know there's a question. Okay. Somebody will do. Acha, how do I go ahead? Okay, thanks. So before I start, let me acknowledge the people who've been responsible for all this work. And most of the work that is on the 2D materials was started by one of my students. As Professor Farsha says, one of my favorite students, and he happens to be a product of AMU. Shamin is now doing a postdoc in Hong Kong. So he's not in the picture. He's not in this picture, but I'll show you. In fact, he started the work on 2D transition metal dichalcogenides in my lab, roughly in 2015-16. That's when we started. While we've received funding from a lot of government agencies, as you see on the left, I was just discussing with the colleagues here But nowadays, it's very difficult to get government funds. So what I've started is to get on to industrial projects. And this being a department of industrial chemistry, I'm sure you have many more options than I have. So some of these companies that fund my research are listed over there. And then we have a very nice central research facility at IIT Delhi and also the DST Sathi facility. So I don't really have to maintain very expensive equipment in my lab. In fact, these central research facilities are open to everybody. Some of the PhD students from AMU also use it. So there, you name the instruments, we have everything over there. Helps a lot in my research, and I don't have to maintain it. That's the best thing. Because, you know, again, maintenance requires time, requires cost. Yeah. So all of the experiments are done at equipment that are housed in the CRF and Sathi. And I must thank all my collaborators over here. So Praveen, Pralay, Shashwata, and Dibya Jyoti for the theoretical inputs. Samit, who taught me how to make these devices. Okay. So I'll be presenting the work today, and the contents of this is about transition metal dichalcogenide. So let's not worry about these contexts anymore. But I'll be focusing a bit on molybdenum selenide and its heterostructures, and then a bit on niobium selenide. So some of the work that has been going on. Now, what are nanomaterials? Okay, what's the definition of nanomaterials that anybody knows? Anybody can just raise your hand and tell. Yeah, please, ma'am. Very nice. So one thing in the nano range. Any other definitions that anybody knows? Yeah? No? Come on. This is some common definitions that I've heard, I've read. At least one? Yeah, that's what the lady said. So any other definition I was asking. So, yes, you have one more. Wow.
Which have different properties from bulk material.
Super. That's a more acceptable definition for me. Yes. Okay, but not necessarily enhanced. Sometimes it can be suppressed also.
Sir,
That's a lovely thing, yes.
nanomaterial shows different properties in different range of size. Like in different size shows different properties.
That's something I was looking for. Okay, so the thing is that it's not important that one of the dimensions is in this nano range, which is defined as 1 to 100 nanometers. If you look at the standard textbooks, where at least one dimension is less than 100 nanometers. What's more important is that the property changes as a function of size. That's very important. Because, you know, I could have something which is 50 nanometers, but then it behaves just like bulk. It's, well, what do I do with it? Okay, even if I call it a nanomaterial, I cannot harness any of its properties. It's just exactly the bulk material, right? There's no change. So what you need is that the property must change as a function of size, and for that matter, this size range can be limited to 1 to 100, but not for everything. You know, you take a look at quantum dots. Now, quantum dots, everything happens well within 5, 6 nanometers. Well, okay, if you're taking some of the infrared quantum dots like lead sulfide or selenide, you can go maybe up to 20 nanometers. And then you have a variation of the band gap as a function of size. But anybody who's not aware of quantum dots, because I heard that there are a lot of UG students and Masters, students away. So if you're not aware, then you just have to, all of you have to raise your hands. Yeah, I want to be on the same page. Are you aware of quantum mechanics? Huh? Are you aware of something called particle in a one-dimensional box? Super. What is the equation? What is the expression, sorry, not equation, expression for energy of a particle in a 1D box? Super. So n square h square upon 8 ml square. Right. Let's get rid of the rest of the things. Let's just worry about 1 by L square. So as you're at a larger length, your energy is small. But you reduce the length of this box, the energy becomes large. If the energy becomes large, so does the energy gap. If you're looking at semiconductors, then semiconductors are typically defined by your band gap, the valence band, conduction band. And this band gap is going to change, is going to increase as I reduce the size of the semiconductor, right? Just from this equation that you just mentioned. As simple as that, right? So your energy levels are going to change and your band gap is going to increase. That is called the quantum confinement effect. Okay. Of course, it depends on what the particle is, right? What is the dielectric constant of that material? How fast the electrons and holes, that's another concept. If anybody has a problem with hole, then do you have a problem with a bubble of air in a bucket of water? Anybody has problems imagining a bubble of air in a bucket of water? You say bubble? Anybody who does not say bubble? The hole is something similar like that. It's the absence of electron. Okay? And so if an electron from an adjacent site hops on, then the hole starts to move. That's how you imagine it, right? Like you imagine the bubble. Huh? And the electron, so once you excite, the electron goes to the conduction band. There's a hole that is created in the valence band, and these two are the ones that are being confined in this box. Okay? The energy levels are of this electron and hole pair, right? And these are the ones that define your band gap, because it goes to the bottom of the conduction band. The hole stays at the top of the valence band, right? Okay. So you have this electron and hole, and then you have the confinement of these materials. And because of that, your band gap changes. As you reduce the size, you increase the band gap of the material. And this happens typically at sizes which are below 6-7 nanometers for most semiconductors. As I said, for lead sulfide and a few others, gallium arsenide maybe, it's about 20 nanometers at the most. So if I go to about 50 nanometers of lead sulfide particle, it doesn't make any sense to call it a nanoparticle, right? Because it's not going to do anything for me which is different than the bulk material. On the other hand, you take some example like platinum or nickel. Those of you who've studied some catalysis in organic chemistry, they know it's always finely divided platinum or finely divided nickel. And that's where the surface area comes into play. And that's a very linear, not a linear actually, cubic relationship that follows, that as you reduce the size of the particle, the surface area keeps on increasing. And as it increases, there are more catalytic sites that come into play. Okay. So you have a much better catalysis. So there, if you're talking of larger nanoparticles, then also it makes sense. Right? So Yes, the official definition which you'll find in books is 1 to 100 nanometers, but make sure that there's a property that changes as a function of size. Okay, so with at least one dimension, so you can have all three dimensions which are confined, and you call it a zero-dimensional material. Don't take this very seriously, very rigorously that it's a zero-dimensional material. A zero dimension doesn't exist, right? Or a one-dimensional material where you have confinement in two dimensions, or a thin sheet where you have confinement along only one direction, or three-dimensional structures, larger structures. So you have a lot of these different kinds of materials, and all these materials have different properties. You can tune them, like we just discussed about surface area, we discussed about the band gap. There are many more. We'll take a look at some of them. And there are loads and loads of applications out here. Okay, I've listed some of those. And I've listed those with a bias because these are things that I work on. All right, but there are loads and loads more applications also. For example, catalysis is one. Yeah. Now, we've already seen, I've already discussed this thing. Essentially, can I make this pointer here? That will be good for the online participants also. So I just discussed this thing with the n square h square by 8 ml square equation. But if you look at a molecule of one material, then it's got this well-defined HOMO-LUMO gap. And if you look at the solid of that material, then it's got this defined valence and conduction band or the band gap. And in between, you have these changing band gap as a function of size, right? And if you look at how you would like to see this band gap, then all you need to do is to record an absorption spectrum. Okay. And if you look at this yellow-orange curve, then you see that the absorbance is at a lower wavelength, whereas the pink curve, the absorbance is at a much higher wavelength, right? Above this wavelength, it does not absorb, which means this energy is less than the energy of the band gap. But at this wavelength, it starts to absorb. And now, having told you all this, which one is a larger particle and which one is a smaller particle? So is the pink one large or the yellow-orange one large? Yeah. Somebody needs to shout that answer. Actually, everybody should be shouting. Otherwise, I've been teaching horrible things. Pink one. Okay, you had 50% chance of passing this quiz. Now, if somebody says the yellow one is the smaller one, then at least I'll have a even distribution. Now, come on. The band gap is small for a large particle. Lambda is inversely related to energy, right? So you're going to smaller lambdas, you're going to larger energies, larger gaps. So large gap happens to be of the orange one, right? So that's the smaller particle. Okay? And once you excite these things, you have an electron, you have a hole. Sorry, ulta ho gaya. You have an electron in the conduction band, you have a hole in the valence band. And Okay, these two are more or less on the same atom, right? They're just, this is just the energy scale that I show with the hand. They are almost on the same atom, maybe on the neighboring atom, right? So they're not far away in space, which means they have a fairly decent attraction for each other. Okay? So now you can think of a negative charge that is attracting a positive charge. And this kind of a quasi particle is called an exciton because it's in the excited state. And sorry if there are any physicists around, but they love to just take some word and put on at the end and say, okay, it's a quasi particle. You've seen phonons, photons, these are bosons. You can name them, but this is an exciton. It's in the excited state. It's the electron hole pair, and they have some bit of attraction for each other. And you can model it just like a hydrogen atom. Huh? So again, you've studied quantum chemistry, you know what the hydrogen atom model is, you have all these individual levels. The hydrogen atom is proton plus electron. Here you have a hole and an electron. So it's exactly like a hydrogen atom that you can model it. Okay? And it will have its own. So the exciton is also there, and if the exciton Bohr radius, like you have the hydrogen Bohr radius, what's the number for that? Come on, in my interview, if somebody doesn't know that, I don't take that person. Yeah. 0.529 what? Super. So, if you think of the hole, okay, it is more or less, the mass of the hole is close to that of the mass of the electron, more or less. It's a bit heavier, slightly, but more or less around of the same order. Mass of the proton is almost 2000 times heavier than the electron, right? Now, what do you expect? The exciton Bohr radius to be larger compared to the hydrogen Bohr radius or smaller? No. See, again, you had 50% chance. See, when you do the hydrogen atom problem, you take the Born-Oppenheimer approximation, throw away the mass of the proton because it's so heavy, right? Now you'll have to use a reduced mass. So that mass comes in. And so the exciton Bohr, and it's in the denominator, right? If in the denominator there's a smaller quantity, then the exciton Bohr radius becomes much larger. So if the Bohr radius of this exciton is comparable to the diameter of the quantum dot, then both your electron and hole, they're kind of trapped inside, right? Your exciton is trapped over here. If, on the other hand, your semiconductor particle happens to be large, then, you know, exciton Bohr radius is like this, so they can go far apart. So there's a huge quantum effect that comes in when you have small particles of the size of the exciton Bohr radius, and that's where you start to see all these quantum size effects. And that's the future of all these quantum materials that you hear. If you've not heard, don't worry. But there's a huge amount of national quantum mission that has come about. Okay. All right. Now, once you have it excited over there, it doesn't like to stay over there. Huh? I'm lazy. I don't know about you people. This fellow seems to be sleeping. नहीं यार तुझे ही देख रहा था. I don't know. Are you lazy? So are the electrons and the holes. They again want to come back and relax. But when they come back and relax, the energy is given out in the form of, well, it could be in the form of radiation. And when you give out this energy, then what you get is fluorescence out of these materials. So this fellow gives you fluorescence which is in the blue region. 460, 70 nanometers is blue. This fellow gives you fluorescence in the almost green region, and 560 is close to yellow, and then you can make even bigger particles and go to red. So these days you have all these quantum dot televisions in, somebody must have seen in the markets here. They're made out of these kind of quantum dots. See, these emissions are very, very narrow. So that's why you get very good color purity, and because of that you can distinguish those colors, and that's why these TVs cost you about 5 to 7 lakhs. So not worth buying, I think. But quantum dots also have applications in other fields such as bioimaging and tagging applications, right? Okay. There's something which we did with these quantum dots, and we were trying to make some core shell structures out of these, and trying to tune the emission properties. So I mean, I don't have to worry about that. There's another thing where we were trying to make some of these quantum dots, again core shell materials, the same thing. But what you do is, if you look at if you look at this schematic over here, okay, this is two semiconductors joined together, okay, and the band gaps of these semiconductors are different, but you just don't know how they are aligned with respect to each other. Okay. The way to think is pretty simple and straightforward. You take two buckets of water, and they have different amounts of water, and then you connect them with a tube. What happens? It comes to the same level. Likewise, in solids, you have electrons that occupy these energy levels. Okay. So in one solid, let's say it's occupied up to this level, in another solid it's occupied up to this level. The moment you connect them, they equilibrate. This top part is known as, the top level is called, somebody can shout the name. Hey, come on, Fermi level. Well, of course, that's the definition is at 0 degrees Kelvin. So the Fermi levels, they align. Okay. It's exactly like that simple thing, water coming to the same level. Fermi levels, they align because the electron would not like to stay in a higher energy state. It will flow over to a lower energy state, and once they align, so the Fermi levels of these two semiconductors, once they align, then I have a band alignment. And this band alignment, the kind that I have shown over here, is called a type 2 semiconductor heterostructure. Now, the type 2 is that the conduction band of this material is at a lower energy than the conduction band of this material, and so is the valence band. So the moment I have an excitation, my electron would not like to stay here, right? The electron comes to a lower energy level, it comes here. The hole would not like to stay here, because the hole or the bubble comes to the top. So the energy level, the lower energy level for the hole is over here. What do you have? You have a charge separated system. You have holes on one material, you have electrons on the other material. What can you use them for? You can think of applications. How did I excite it? By shining some light onto the system. Yeah? The absorption spectrum that I show you is because I shine some light. So I excite this by shining some light. And what applications you can think of? So charge separation, right? So solar cells is one. Anything else? Not emission. I'll come back to emission. Just give me one moment. How many of you are doing a PhD over here? Super. How many of you have actually worked on dye degradation? What is that? In general, what is that thing called? Huh? Photodegradation. So it's photocatalysis. Okay. What do you need for photocatalysis? You either need to oxidize the dye or you need to reduce the dye. The electron and hole, when they're separated, they can be used to achieve these things, right? So photocatalysis is one thing. Photovoltaics, as you said, is another thing, because I need separated charges. I need these separated charges and I want them to go in an external circuit. Yeah, that's the next step, how you would achieve that. Photodiodes, for that matter. Yeah. So you can think of these kind of applications where you need separation of charges. So when you design a type 2 kind of a heterostructure, you already have some applications in mind, and what I'm showing you is, of course, methylene blue dye degradation results over here with these kind of heterostructures. Okay. Now coming back to what you said about emission. For light emission, what you want is that the electron and the hole should recombine. Now they are far away. So what do I need? I want them to be on the same material. So instead of having a type 2 heterostructure, what I want is, now look at my hands, my fingers rather, is a material like this. If I have this material, then both the electron and hole will stay in this one, right? On my left hand. Once they stay on the same, then it's easier for the electron and hole to find each other. It's much easier for them to recombine. This is called a type 1 kind of a heterostructure. Okay? And there's type 3 and type 4 also, we'll not worry, but those who are interested can definitely Google up. Okay. Can I say okay and it goes away? Super. All right. Now, moving over to what I wanted to tell you more about is these transition metal dichalcogenides. And they've been known for almost 60, 70 years, definitely, maybe more. In fact, I worked with them when I was doing my BSc practicals. And I'm sure everybody's worked with a burette or a pipette. And then there are markings on those burettes and pipettes. And they fade away. If you've noted, they fade away. Yeah? No, not work so much to make it fade away. And then I went to the lab technician and I asked him, well, it's faded and I cannot read it properly now. So all he did was he took some black powder in his hand and it rubbed it against the burette, then washed it off. And again, those were dark. The lines were filled with this dark powder. It was dark and I could read it very easily. You know what that powder was? It was molybdenum sulfide, MOS2. Not 2D material, but bulk material. Okay. It's been also known as a lubricant. It's a solid lubricant, much like graphite, right? The layers slide over each other. It's known to be a lubricant. So, this has been known, it's been worked on. But after the discovery of graphene, 2004, Novoslev and Geim, people started exfoliating everything. Okay. And the method is pretty simple. I don't know if Professor Liu told you about it. They explained you should try it yourself. Take a block of graphite, it's very cheap. Take a scotch tape, aise nikalo. Take another scotch tape, put it on that. take another scotch tape, put it back. What you're doing is just reducing the number of layers. And at some point of time, you tend to get a monolayer. So, these are also layered materials. In fact, if you look at the structure over here, okay, let's look at this particular structure first. The metal center is the silver one in this over here. It's surrounded by 6 chalcogen atoms. And 6 means the first thing you say, okay, it's octahedral, or it's trigonal prismatic. And if you look at the crystal field stabilization, then trigonal prismatic is more favored. In fact, what people also did was to use lithium in order to exfoliate it. What lithium does is to give an electron to the system. And when an extra electron goes, right, now there are 3 electrons in molybdenum. Molybdenum 4 plus has just 2 electrons, right? Now when you get 3 electrons in molybdenum, then it's the T2G level that gets stabilized more than the trigonal prismatic, which is 2 above 1, right? I don't remember the symmetry notations, but this is 1, then 2 levels. So, 2 electrons would be here and 1 electron would go up versus 3 electrons in the T2G level. So, the octahedral phase gets stabilized because of the electron that comes in through because of lithium, and this twists, okay. But otherwise, if you don't have this lithium, then you have these 2 electrons which go in the lowest level of the d orbitals, and therefore it's a trigonal prismatic coordination, and it continues like this in the sheet. And all these sheets, all these layers are held to each other by van der Waals forces of attraction. And what are these van der Waals forces? It's essentially the d orbital interactions between the sulfur or selenium, and these are all sulfides, selenides, tellurides. Well, I've not listed everything. Not oxides. Oxides don't form this kind of a layered structure. There are other oxides which form, but not in this case. Okay. All right. Now, all you need to do is to apply some small bit of energy, and you can exfoliate them, right? And once you reduce the number of layers, then it is again something that you're doing by reducing the size of the particle, right? So, there are quantum confinement effects, so you have a tunable energy band gap. There's something called indirect to direct band gap crossover. Those of you who know, when you plot the K, E versus K diagram, then it's not a straight line, but it's somewhere over there at a different K point. Being a chemist, I try to understand it more easily by saying that, look, earlier what I had was these d orbitals of sulfur, which were bonded to each other, and they were forming the bottom of the conduction band. They were unoccupied orbitals. Now you have removed them. So that bond no longer exists, those states no longer exist, right? And therefore, when you have just one monolayer, what you get is a direct band gap, which is something is happening. So you want to take care of it. Oh. They're connected, right? अच्छा कुछ आ गया देखिए देखिए डॉक्टर साहब बता देना मुझे कब रुकना है, वरना आपको भूखा रखूंगा. All right. Yeah, we are online now. We are online. Yeah. So what we also have is very strongly bound excitons. I did not mention this, but well, when I said the electron and the hole, I call that an exciton. The exciton has a binding energy, and that binding energy is nothing but the Coulombic energy between them. Q1, Q2 by, come on, R square. Okay. So, well, that's the force. Okay. So, the Coulombic energy is 1 by R, right? So, this attraction is also called the attraction between the electron and the hole. That's called the excitonic binding energy. And if it's strongly bound, which means your exciton, your electron and hole, they want to move in the solid because it's in the bands, and the bands are delocalized over the entire solid. So they can move together. If they can move together, they can recombine together, they can go to another material together. If they move separately, well, that's also useful. That's useful for all the other applications that we discussed, right? And the mobility of charge carriers is high in the plane, okay? Because it's this continuous band, there's no disruption, so they can very easily move in. Of course, across the planes, it's much difficult. There's a lot of tunneling barrier over there. And now, you have so much of surface area in these 2D materials. A few layers or a single monolayer doesn't matter, but there's so much of surface area that the catalytic activity increases a lot. Okay. So, I'll show you applications of these transition metal dichalcogen that range from electronic applications, optoelectronic applications to catalytic applications. Okay. And I'm stuck once more. So, you did something last time. You could teach me the tricks. हाँ ठीक है, हो गया. I learned it, ma'am. So if you look, it's okay. I managed, thanks. If you look at these applications in the literature, they have been classified as basal plane applications, which are most of the optoelectronic kind of applications, are based mostly on the electronic structure, and the edge site applications. Now, if you look at this materials, then you'll see that in the most of the material, the valencies are completely satisfied. But if you go at the edge sites, if you look at somewhere over here, this one, then you can see these two red atoms, they have unsatisfied valencies, dangling bonds. The moment you have dangling bonds, you have a huge surface energy over there, and that's where all the catalysis occurs. Okay. So all these catalytic kind of applications are based on the edge sites. Now what Shamim did, he's a really smart fellow. I think you should be proud of him. What he did was that he said, I'll make these molybdenum selenide nanosheets, and that's by chance because the method that he chose, that was by chance, or I would say that was because I have been working as a colloidal chemist. So I've been using mostly colloidal methods. Had he used exfoliation or something, he wouldn't have gotten these results. So what he did was, he took these precursors, injected at a high temperature of some 260 degrees. This is something that you can just get in the market. Earlier he used some heptamolybdate to make the ACAC. ACACs are available now. So you can just take the selenium precursor, which is a mixture of selenium and oleamine, inject these two in a high boiling solvent, octadecene or oleamine. These are long chain carbons. So, okay, and you heat it for a few minutes, or you can increase the time. And what you get is molybdenum selenide nanosheets. And if you look at all the other methods, see chemical vapor deposition, um, pulse laser deposition, or molecular beam epitaxy, instruments that cost you multi-crores of rupees, they give you very nice sheets. If you've taken a look at some of the transition metal dichalcogenides photographs, you'll see these nice triangles. And if you look at the TEMs, you'll see very beautiful arrangement of atoms. What we get is these horrible crumpled sheets. ऐसे लगता है किसी ने पेपर को ऐसे करके फेंक दिया. Why? That is because of the inherent nature of this colloidal chemistry, that it introduces defects into the system. And these defects are absences of selenium atoms. Okay. So the moment you have defects, if you think of, take a look at this particular line, it's an absence of selenium atom. Now you think of molybdenum that is sitting inside, it wants to bond to its selenium, and you have a missing selenium atoms. Then it tries to attract the next nearest neighbor seleniums. The moment it does that, those things come close. So the sheet, instead of being straight, it starts to fold like this. And you have a lot of these defects. So this is really a defective piece. Well, but then defects were good for something. They were good for all the edge site applications, because there you have dangling bonds. And lo and behold, he does these experiments and gets amazing results out of this. What I'm showing you is something I think we are also going to demonstrate in the afternoon. But let me explain this. It's very nice that Professor Zain has already explained these semicircles. So what you have over here, take a look at the pink curve. Okay, you are applying a voltage and you are measuring the current. So just think of these two electrodes. You are applying a voltage and you are measuring a current. Okay. Although this is done with a 3 electrode system, so that the voltage and current do not interfere with each other. But for sake of simplicity, let's just think of these 2 electrode systems. Okay. One is a platinum, and then the other one is a glassy carbon. On top of it, you can put any material. So, all right, my question to you, if I put platinum over here, then at what potential do you expect hydrogen to come out? So you have 1 molar acid, okay, and I have platinum electrode here, I put platinum electrode here. What is the potential that is required for hydrogen to evolve? What it's going to do? It will take an electron from the electrode, H plus electron gives you H, 2 of these H will combine and you get hydrogen out. So what is the potential that is required? Okay, I think MSc and PhD grads are too old for this question. Is there somebody from the 10th standard or 11th perhaps? Why? Come on, that's the definition of the standard hydrogen electrode. If you have platinum, you don't, at 0 volts, this reaction is happening, right? Now, the whole thing is that ideally it's not 0, okay? Ideally it's 0, practically it's not 0. And so you need a slight overpotential over here, okay? You'll see that about 10, 20 milli electron volts. okay, this is in volts, the scale is in volts, is when it starts. And what people report in the literature is when the current develops to 10 milliamperes per centimeter square. Okay. So platinum by far is the best thing, but unfortunately it's too expensive. Huh? I work with gold and I work with platinum in my lab, and there are a lot of girl students, and I'm always scared that sometimes I'll see a new jewelry on them. So it's pretty expensive over here. And that's why you shift to some of the cheaper materials like molybdenum selenide. Okay, jokes apart, this is molybdenum selenide bulk, and that requires an overpotential of about 500 millivolts, 0.5 volts, to get minus 10, or minus is just the sign convention because you're flowing electrons over there, right? 10 milliamperes per centimeter. The moment you exfoliate it to, this is 6 monolayers and 1 monolayer comparison, so don't worry about that. The moment you exfoliate it, this potential falls down drastically, and that is because you've provided so many of these sites, right? So many of the defect sites that are present on the surface after exfoliation, that your potential just drops. So you can do the same thing at much lower costs. All right, these devices are pretty stable, and I think all the EIS measurements is something that Professor Zain has already taught you. It so turns out that you see the red curve is for the one monolayer, and because it doesn't have to tunnel through, you know, I've shown a schematic. The electrons don't have to tunnel through. It's a much faster process. It happens with much ease, and therefore it offers least resistance, least impedance to be correct. Okay. The Tafel slopes are something which tell you how easy this reaction is, because you don't want to be operating at 10 milliamperes. If you really want to produce hydrogen, you'll go down to 50, 100. Well, actually, for the commercial electrolyzers, what you need is about 400, 300 to 400 milliamps. And at that potential, the Tafel slope is exactly telling you the inverse of this curve, okay, except that it is per decade of the current. If you look at this, the mechanism is pretty straightforward. You have H plus that gets absorbed on the catalyst surface, okay, and then another H plus that gets absorbed on the catalyst surface, okay, and these two then recombine. Well, of course, the plus is taken away by the electron, it becomes an excited, so H atom kind of thing, and they recombine, sorry, they combine and give you H2. In the Heroski step, the H plus has to find this this hydrogen atom, okay, right. So this one happens to be a tougher step. It requires more potential. This is a much easier step. And now if I have created so many defect sites on the surface, you know, which one is going to be more favored? Is the Tafel mechanism. If the Tafel mechanism is favored, then you will have much more hydrogen evolution reaction. And that's what is happening, that the slope of this, the inverse of the slope of this is a small number. The smaller the number, the more hydrogen is coming out at larger potentials. So you need this. Somehow you promote the Tafel mechanism. So you can, well, of course, Shamim did not stop here. He said, let me go ahead and let me make some heterostructures of this material, because you've made one material, okay, you can do as much with it. But now I've been making heterostructures for a very long time, and Shamim said, I'll make a heterostructure with cuprous sulfide. Why? Why? Because when you're making heterostructures, then you're growing one atom on top of the other, right? One material on top of the other. So it must have a good lattice matching. If you look at this 0.329 nanometers, well, C is the growth direction. It's a hexagonal structure, so C is the growth direction. I don't need to worry about that. The B direction 0.329, so it's in the AB plane that it will grow. And here it's 0.379. That's pretty close. That's a lattice mismatch of about 6.5, 6.6%. Okay. Which is pretty good for a growth. Okay, there'll be some strain. The other thing is, okay, look, this fellow is a semiconductor, cuprous sulfide happens to be, if it's actually cuprous sulfide, it happens to be a zero band gap material. So maybe I can also get some interesting properties. Well, of course, he didn't form cuprous sulfide. What he formed was copper 1.97 sulfur. So it has some vacancies and it's a different kind of a material. But what you have over here is you take these defect-rich molybdenum selenides, and since it has defects, it's hungry to quench those defects. If it reacts with selenium, it also reacts with sulfur. So what Shamim does is put some dodecane thiol. And these dodecane thiols, they go and occupy the vacant sites, the defect sites. If you look at the Raman spectrum over here, this is the A1G band, this is the E2G band. Sorry for not labeling them. They are present. They are present in all these 2D transition metal dichalcogenides. But this fellow in between is because of the defects. And it's present only when you do a colloidal based synthesis. Okay, and it's been reported, it's been characterized. So when you do a treatment with dodecane thiol, the intensity of this fellow just goes down, telling you that most of the dodecane thiol has passivated these vacant sites. And then you throw in cuprous iodide. Another question for the 12th standard students. Copper, does it have affinity for sulfur? All of you have done group analysis, cation analysis. नहीं किया? Nowadays you have this KIPS apparatus where you pass H2S or no? No, it's allowed? It smells too much, huh? No? Have you used a KIPS apparatus or not? What is the first thing that precipitates out? Copper. If you have copper, it will precipitate out as copper sulfide, black. After that comes lead. नहीं? भूल गए? इसीलिए मैं कह रहा था कि you need some fresh people. It's already 6 years, 7 years. कब किया था 12th? I think you must have done BSc also. In fact, now you've all made nanoparticles, let me tell you, using this KIPS apparatus. There's another cation, cadmium, which was also precipitated as a sulfide. Now, I think I'm going to put a lot of pressure on your memories, but when you pass this H2S, and if you had cadmium, do you remember some very peculiar features of that? It came out as a yellow color, yellow, but you know, if you went with that yellow color and tried to filter it, it just passes through the pores. You had to put more H2S and make it almost orange colored. In fact, when you started putting H2S, it was white. Pehle to it's a transparent solution, right? And then it there's some turbidity comes in, it's white. It's from white, it becomes yellow. From yellow, it becomes orange. And when it's orange, only then it sits on the filter paper. What's happening? Why does it pass through the filter paper? Because the size is small. Why does the color change because the size is small? Because the band gap is different. Orange. If you see something orange, what does it absorb? Which color does it absorb? Green. Right? If you see something yellow, what does it absorb? Blue. यार वो एक कलर व्हील होता था हाँ complementary color wheel, you could make that out. Blue. If you have white, if you see something white, what does it absorb? It doesn't absorb anything. It absorbs in the ultraviolet, if at all. Black absorbs everything. So black absorbs from the infrared all the way in the visible. White doesn't absorb anything. Yes, it might absorb in the ultraviolet region. Ultraviolet region absorption, large band gap. Blue, no. When it's absorbing blue, it's a smaller one. When it's absorbing green, it's even smaller. Particle size is growing in that direction. So you all have made nanoparticles even long before you've known that. Okay. So Shamim, what he did was he put some cuprous iodide, and it has so much affinity for sulfur that it reacts immediately, and it forms these kind of heterostructures. So if you look at these TM images, these are molybdenum selenide sheets, and on top of that you have cuprous sulfide. Okay. And in order to establish all that, you do something called an X-ray photoemission. What you're doing with an X-ray photoemission is that you're shining X-rays, and any solid for that matter has its electron levels, right? And is it time for me? Oh, okay. It has its electron levels, right? And if you think of the valence band, then all those levels are involved in bonding. But if you think of the deeper levels, the core levels, what you call, they're not involved in bonding. If they're not involved in bonding, they're more atomic-like, because they're not delocalized over the entire solid. They're on the same atom. So they're very sharp, right? So if I shine X-rays and I pick up an electron from this, then I'll get a very sharp peak. And that peak is going to be very much at the same position. Okay. But if I have, let's say if I have an element that is in its oxidation state is 0, okay. So I will get this electron at a given. So electron comes out, then it has some kinetic energy, right? I can calculate that kinetic energy. I know what is the X-ray energy. So all I need to do is X-ray energy is h nu. H nu minus the kinetic energy is the binding energy. So I know what is the binding energy of this core level electron. So the binding energy is something for for some metal which is 0 valent, or it's, let's say, copper 0, so as to say. Okay. I oxidize it. If I oxidize, I take out 2 electrons. So the nucleus is now attracting everything with a larger force. It's binding strongly. So its binding energy increases. On the other hand, if I put in 2 electrons, which is difficult to do on copper, on oxygen for example, oxygen in 0 and oxygen 2 minus. So if I put in 2 electrons, then its binding energy is going to decrease. So this is how you analyze your XPS spectrum. Now if you do this, the instrument doesn't know whether it's copper in this state or molybdenum in this state or what. It gives you a one single signal, right, when I'm monitoring. So when I'm monitoring at the range which belongs to molybdenum, 3D. Now 3D is a core level for molybdenum, right? 3D is not involved in bonding. 4D is. Yeah? So 3D is a core level. So I get this complex signal, and then what I need to do is to fit this with the least number of functions. The functions are, the easiest functions you can think of is Gaussian, but what we actually use is a sum of, it's a combination of Gaussian and Lorentzian functions, because Gaussian is for the width of the peak due to the instrument, and the Lorentzian is for the lifetime broadening. Okay. So it's called a Voigt function, V-O-I-G-T. Anyway, just think of it as a Gaussian, which is much easier for people to understand. You take the minimum number of functions that are required to define this and you fit it. Okay. Now 3D, for example, you take a look at the blue curve. So this is 3D 5 by 2, that's 3D 3 by 2. When you fit, you have to take care of a lot of things, because there's a ratio between 3 by 2 and 5 by 2, right? And everybody knows what that ratio is. That ratio has to be maintained, right? So all these peak ratios need to be maintained. The widths need to be maintained. You can't just, one thing can't be just this big and the other one can't be this small. And I'm especially telling you because those of you who would do XPS, and since you all, a lot of you would be working with materials, this is a very important characterization tool. So when you do a fitting, then keep these things in mind, because you can fit anything. You can fit a rabbit to an elephant, I think. But when you do it, you need to keep all those things in mind. Okay. So what you get is these two peaks for molybdenum, and molybdenum is mostly bonded to selenium, so naturally I'd say fine, this large peak should be the one that is bonded to selenium. The small peak should be the one that is, I've also added the dodecanethiol and now it's formed cuprous sulfide, but that sulfur has bonded to molybdenum, so it should be. And also, if I look at this, it's got a larger binding energy. Now sulfur being more electronegative, the molybdenum that is bonded to sulfur should have a larger binding energy. So everything makes good logic over there. Only then you propose such a model. Of course, there's another sulfur. Now the poor fellow has its 2s level at this position, so it has to be there. So you'll also have to worry about taking care of that one. Okay. So molybdenum is bonded to selenium, molybdenum is bonded to sulfur. Selenium has only one feature because it's just bonded to molybdenum. Copper has only one feature because it just bonds to sulfur. Sulfur, on the other hand, has two. One that is bonded to copper. Most of the sulfur is bonded to copper in that nanoparticle that is formed on top. And a little bit that is bonded to molybdenum also. Okay, and that's some bit of sulfur which gets oxidized. Okay. So that's how you characterize all these things. And then don't ask me much about this because I'm not an expert with the theoretical calculations, but these are fairly straightforward to do. Okay. I can do that. I really do not know the nitty-gritties of these calculations. But these days, for example, Quantum Espresso, it's available for free. You can download it, you can do it. They also have servers online, so you can submit your jobs and do it. And to learn this, it takes if you've done your MSc, then it takes not more than a week to learn this. After that, everything is a black box for me. So anyway, what you do is you make this heterostructure and you calculate the electronic structure. You get the density of states, and what you do is, you see, the blue one is the total density of states. The red one is molybdenum. See, it does not have any density at the top of the valence band. Whereas the green one is because of copper sulfide. It has a density at the top of the valence band, right? The red one over here has density at the bottom of the conduction band. Molybdenum selenide has density at the bottom of the conduction band. It's overlapping with the blue one, the red thing. The green one doesn't have, which is cuprous sulfide. This is exactly a type 2 kind of a heterostructure. Okay. And you align it with the normal hydrogen electrode, and you'll see that it's possible to get the electrons and holes both out of the system, and therefore do an oxygen evolution reaction and a hydrogen evolution reaction, both from the same material. And therefore, these are the results of oxygen evolution reaction, which surpass the standard, the industry standard of iridium oxide. Iridium oxide and ruthenium oxide are the ones that are being used in the electrolyzers today. I hope everybody is aware of the green hydrogen mission. India is going strongly for that, and they are setting up so many electrolyzers. Soon, you know, you're going to have a very huge hydrogen. It's a very clean fuel, to understand that. Just burns and gives you water. So, but the whole problem is, today to make hydrogen, you need 600 rupees for 1 kilo of hydrogen in Europe. In India, you need 280 rupees. That's just because of the difference in the labor cost. Okay. But that's not economically viable. It's just that the government is giving a push to theek hai, everybody's setting up these electrolyzers. Economical viability comes when it comes below 80 rupees a kilo. And how do you make it happen? You don't have immense sources of platinum resource. I mean, it's limited. Iridium, ruthenium, these are limited. So you need to look for cheaper catalysts, earth abundant catalysts, one thing. You need to perhaps look for not complete water splitting, but doing something else with it. For example, one of my friends, he works on lignin. Lignin, ये जो पराली है, I hope people, I mean, people don't burn here, but you know, in Punjab, Haryana, there's so much of people there, they're burning it, right? So instead of that, converting it into something useful, oxidize it and convert it into something useful. Or get rid of the oxygen evolution. Oxygen evolution costs you 1.23 volts. That's the thermodynamic potential. 0 volts for hydrogen evolution, 1.23 for oxygen, right? You could go for urea oxidation reaction instead of the oxygen evolution reaction. There, the potential is, I think, 0.4 volts. Don't quote me for the numbers. So, one really needs to work a lot on this before the hydrogen economy can be economically viable. And for those of you who are looking out for jobs and all, so be on the lookout for jobs in this sector. Yeah. Hydrogen is a very big thing that's coming up. Okay. All right. I'll not go into more details over here. We can also do the hydrogen evolution. There's a mechanism also, because these are type 2 kind of heterostructures. We also made some very interesting photodiodes. And if you look at these photodiodes, then you see, this is current and that's voltage, except that it's plotted on a log scale. So to clearly amplify these differences. If you look on the right side, you see both dark and bright under illumination, they are exactly the same. But in the reverse bias conditions, this is your dark and that's your bright. The on-off ratios are 10 to the power 5, 1 lakh times. Okay. So you have a light, you get a current. You don't have light, you don't see a current. This is a photodiode. This is how it works. And the best thing is it can detect infrared radiation. Okay. So these are some of the applications that I think we can go on, but I think I need to stop at some time. So 10 minutes? Okay. All right. Yeah, this is another interesting thing. Since Shamim was on a spree, he was making these heterostructures. He said, I want to make heterostructure of molybdenum selenide with cesium lead bromide. And cesium lead bromide happens to be a perovskite material. I'm going to tell you more about perovskites in the next lecture. And cesium lead bromide, a lot of other people were working in my lab. And it's very bright, very nicely colored. And if you've heard of the solar cells, then you must have heard of the perovskite solar cells. I'll tell you in the next lecture. So he said, I want to make a heterostructure, but he tried many times, he failed. And that failure I'll tell you in the next lecture, what happened with the failure. But then he devised a method. He said, I am not being able to make this directly, let me do an indirect thing. What he did was, remember the dodecanethiol, it goes and sticks onto MOSE2. So he used another molecule, it's called an aminothiophenol. Okay. It has a thiol and that thiol goes and sticks onto the MOSE2. Okay. So that's thiol bonded over there. The amino part is free. Okay. So given some time, you throw in this cesium lead bromide. The cesium lead bromide is actually stabilized by oleillamine. The oleillamines, they leave and cesium lead bromide comes and sticks over here. And you can see these in the TEM images. Okay. And this is the same Raman thing that I was showing you earlier. So this sticks, and okay, it's not that it's just sticks over there. We've characterized it well enough. We've washed these about 4 to 5 times, so it just sticks over there. And then again, theory from Shashwata and Pooja, they tell that it's a type 2 kind of heterostructure once more. So it's good for, you know, the same kind of applications that you're looking at. But this type 2 heterostructure is not a great one. You see, when you're designing these, and if the electron has to jump so much, one, it's not efficient. Other, you're losing so much energy, right? Because once the electron jumps here, only then you can utilize. Okay. So if you had to catalyze something which requires this much energy, you will not be able to do it, because now you have electrons here and the holes here, you have only this much energy, right? So when you design these kind of heterostructures, make sure that it's not such a huge jump. But anyway, yeah, as I said, that these are very well stuck onto the molybdenum selenide. If you look at the fluorescence of cesium lead bromide, then these are very fluorescent particles. They look beautiful green particles. You make the nano heterostructure, the fluorescence gets quenched because immediately the electron and hole, because of that type 2 kind of heterostructure, the electron and hole, they get separated and they cannot recombine. And if you actually just use a mixture without the 4 ATP, then because of collisional quenching, some of the fluorescence is lost, but not to that extent. Okay, these are the time resolved fluorescence spectra, which also tell you the same thing, that if you have, so if the fluorescence gets lost, if the charge carriers, the excited charge carriers they dissipate away faster, then your fluorescence lifetimes come down very fast. Okay? And they do not if they do not dissipate fast. Okay? Okay, all that is fine. We make these same devices, photodiodes, and look, this is the cuprous sulfide. And that's the dark current for cuprous sulfide. And that's the dark current for MoSe2 cesium lead bromide. And this is the bright current. What is the difference that you see? You're getting almost similar currents. The dark current has gone down. Okay. And the bright current over here, you're also seeing a current at 0 volts. This is called a self-powered photodiode. Why is it self-powered? Because of the fact that cesium lead bromide is a photovoltaic material. Photovoltaic is that it generates the voltage itself, right? I'll come back to more of photovoltaics in the next lecture, but I think I can stop here rather than going through more. I think I can stop here, right? Even if there are online questions, yeah. Bolo, I'll repeat the question for everybody. Why only three dimensional? I mean, there are 0D, 1D, 2D, every 3D, yeah. Three dimensional material, calling it a nanomaterial, I mean, there people call it, yeah. It's a bulk material. So I guess the thing is between confinement and non-confinement. So if it's not confined, huh? Yeah. Yeah, 3D material, as far as the electronic properties are concerned, they are just like a bulk material, but perhaps just the dimensions. Please. Can I see it here also? No. There are 5.
This is question. Sunlight can be used to prepare. Yes, sir.
Can they speak? No. Can.
Otherwise, we have to unmute. That may cause some noise also.
Acha. Mehrush. Mehrush is asking, how do we decide the best method to prepare the heterostructure? CVD, PLD. Okay. So what we used over here is just colloidal chemistry methods. Okay. Growing one material in the presence of the other. Okay. So let's say we made molybdenum selenide particles, and then we put some DDT on top of it, and then added some cuprous iodide. Okay. Now the best method is something I cannot comment on. There are various methods. Each of them have their own advantages and disadvantages. If you talk to any device physicist or device person from the electronics background, I'm sure that person will not like the colloidal chemistry methods, because so many chemicals are involved over there. They prefer the cleaner methods of CVD or PLD or MBE or those kind of things. But yeah, everything has its own advantages, disadvantages. For me, using the colloidal methods, it's more versatile. and cheaper also. Let me see. There are some more. Huh?
How to decide one more
Ah,
question?
this is what I just. Sunlight can be used to prepare it. I
Anyone have a question?
okay. Oh, she was also answering. Okay, good. Photocatalytic was the right answer.
There is one more
Yeah,
question.
yeah.
Are there any trade-offs when using nanomaterials in optoelectronics? Like we gain some benefits but also lose something in return?
Um,
Yes, this one.
what do we lose? Something in return. Uh, yeah, yeah, good. So, no, I don't have much idea about this. I'm sure there are trade-offs. On a lighter note, I can say that you lose a lot more money when you buy a QD television. So, although you have more picture clarity, no, no. But I'm sure there are trade-offs, and one should look at that. Nanotoxicology is something that a lot of people study. All right. Yeah, I still am sticking to science, not gone over to policy. So those kind of questions are difficult for me to answer. A student like me wants to start research in semiconducting nanomaterials. What would you suggest as the first step? Jump in. Just contact somebody and come and, come for a month, 2 months and see what is going on. You might lose your interest. No, no, no. But come to any of the labs. Just come and work for 1 or 2 months.
Anything, the TMGs.
This graph again, last second one.
This one?
No, sir, second one.
Oops. Just a moment. This one?
Yes, sir.
This graph is too crowded for explanation. But okay, what I was saying is that I'm comparing this with cuprous sulfide, MoSe2Cu2s and MoSe2 um, cesium lead bromide. Okay. And then of course, just MoSe2 and just cesium lead bromide, they are much lower. When you make the heterostructure, you've gotten a type 2, so there's a built-in electric field that has come in. Then uh, the other thing is when you make a cesium lead bromide, for cuprous sulfide, you do not see current at 0 volts. Normally you should not, right? But when you have cesium lead bromide is a photovoltaic material. I'll discuss about the photovoltaics. So when you have cesium lead bromide, then you see current at 0 volts also. This is about 0 volts, right? But you're seeing a lot of current over there. So that's something which is called a self-powered photodiode. Just a nice name for something which is obvious. I mean, it's photovoltaic, right? But if you want an explanation of this fellow, then I think this is a much better curve to see, where it's just two curves showing you without light and with light. And it's a diode because it works only in one direction. In this direction, there's no effect of light, right? So the charge carriers that were moving in dark are also the same that are moving in light. But in this direction, which is reverse bias because this was a lower current. Well, I'm just assuming that you know what a diode is. Huh? a PN junction diode. If you put a positive at P and a negative at N, then you have the charge carriers moving. If you reverse it, then you don't move. So this is reverse, where it doesn't move, and this is the forward, where you have a higher current, it moves. Right? Whether you shine light or not, it's the same. Okay? And when you shine light over here, then you've excited these from the valence to conduction band and you've allowed them to move. So this is what a photodiode is. In one direction it is affected, in the other direction it's not. A diode in general is in one direction. All right, you'll have more of me after lunch, so you don't need to exhaust yourselves. ठीक है डॉक्टर साहब? और है कोई ऑनलाइन? नहीं. All right, so we'll meet after lunch. Dr. Zain, I think you'll announce the time and all. Thank you.
Thank you, Professor Sapra, for a very insightful lecture. Give a huge round of applause for Professor Sapra. He'll be delivering one more lecture in the afternoon, then there will be a tutorial for which we'll bring the machine here also. It is a small machine, the cyclic voltammetry and potentiometer, that through that machine we'll explain you the working and how we can perform HER and other studies. Now it's time for lunch.